It's so hard just to read from a book that
Okay, let's get started. So I started like with this sequences and series. We kind of started slow at first to make sure we really understood the basics, and that's important. But like now stuff comes quickly, and you have to go back and you have to review every video, your notes, so because now we're just adding and adding and adding lots of new ideas every time. Okay, so make sure that you're reviewing and not forgetting the things we've done before, because in the end you have to know it all. Okay, so here we go. So the next thing we're going to talk about is what's called alternating series. Alternating series. So here's the idea of an alternating series. Make sure you're thinking and listening, not just copying. Okay, an alternating series has terms that alternate between positive and negative values. All right, so it comes from an alternating sequence. So in our sequence, you get a positive, then a negative. We saw those before, right? Positive, negative, positive, negative. So this is how it's commonly expressed. -1 to the I, or I plus 1, or I minus 1. BI, where the sequence BI has all positive terms. So this is the thing that makes it alternate, right? We saw that before when we first started doing sequences. And this could be -1 to the I, or -1 to the I plus 1, or I minus 1. So the BI is all positive, and then we have that thing, which makes them alternate, right? Because whenever the I's are even, you'll get positive. Whenever the I's are odd, you'll get negative. Does that make sense? Okay, so I want you to do this. I want you to write the alternating harmonic series. The alternating harmonic series, both with sigma notation and expressed as its meaning, like a third grader would understand. And I want you to make sure the first term is positive. Make sure the first term is positive, okay? So we've got to remember what the harmonic series is. Now I want you to write the alternating harmonic series with sigma notation and in its meaning, right? Like a second grader would understand. So see if you can do that. Alternating harmonic series. Chris, any luck?
No, I'm like harmonic series.
Okay. Lucas.
I said -1 to the I times 1 over I cubed.
1 over I cubed. Okay, is that the alternating harmonic series? Lauren, what do you think? You agree with that? What's that? I to the first power instead of cubed. What do we think? Should that be a 3 or something else? Should be 1? Yeah, so the harmonic series is just 1 over I. And then we need summation. So how do we do? Is this the alternating harmonic series? Anything? Yeah. So if we want the first, what's the first term here? Positive or negative? It'll be negative. So how do we fix that? You could do +1 or -1. Doesn't matter. So I'll just do -1. And that'll make, when I is 1, you get -1 to the 0, so then the first term will be positive, and then the even terms, the even I values will give negatives. All right? And now I want to write that thing out. So look how scary that is. Look how smart you are, right? See all those scary math symbols? You're so smart. What does that mean? What does that mean? Okay.
-1 to 1 minus 1.
Okay. Okay.
Plus -1 to -1 over 1.
So let's simplify this. So we get the feel for what this is. So it's what? 1 plus or minus half plus a third, alternating harmonic series. Does it make sense? We good? So that's what we said. All right, so write the sequence of partial sums, and we want to ask, does the series converge? What about the non-alternating harmonic series, just the plain harmonic series? Did that converge or diverge? Remember? Harmonic series. Did it converge or diverge? So this is an example of, got to keep track of everything we've done. We show that it diverges, right? It diverges. Even though the sequence goes to 0, this was the example we used to show, if the sequence goes to 0, that's not enough to say the series converges. This is our first example of where the sequence went to 0, the p sequence with with p equal to 1, but then when you add them all up, you still gets infinitely large because we could always get a 1/2. Remember, we took twice as many terms as before, and we always got something greater than a half. So essentially, we could keep adding halves forever, 1/2. So no, the harmonic series did not converge. So then the question is, what about the alternating harmonic series? Does it converge? So let's write the sequence of partial sums. Who can tell me that sequence? Andrew, can you tell me the sequence of partial sums? Yeah, for this.
1 plus -1, then 1 plus -1/2.
Plus? So start from the beginning.
So
1.
and then 1 plus -1/2.
Sure. Yep.
Then 1 plus -1/2 plus 1/3, and then so on.
All right, good. So the harmonic series did not converge. What about this? Does this converge? Or can we just say, because the harmonic series doesn't converge, the alternating harmonic series doesn't converge? Or is there an observation that you could make about this to... Any ideas? Is it worth looking into? Is there a chance it could converge? Why? Why is there a chance it could converge? Yeah, because before we were adding all of them, and now every other term, what happens? We subtract. So there's certainly a chance here. So let's see what happens. So watch. What's the first partial sum is? 1, right? So here we are at 0. First partial sum takes us to 1. So here we are. There's the first partial sum. S1. And then, what's the next partial sum? Takes us back to a half, right? Because 1 minus a half is positive 1/2. So here we are at S2. And then what? From there, we're going to add 1/3. And that's going to put us somewhere about there. There's S3. And then what next? So this is S2, 3. This is S4. So I'm going to subtract a 4th, and I'm going to end up somewhere about there. And what do we say? The limit of the sequence of partial sums is the same as? Sum of the series, right? The limit of this is you could take this sequence all the way out and look at all the terms. It's going to converge on, right, the same as the series. What do we think? Converge or not? Absolutely, because every partial sum is between the last two. So it keeps getting crunched down. And so it's going to converge somewhere. We're going to keep having a shorter distance back. And it's somewhere in here, it's going to converge. So this is a really important point, that when you have an alternating series, you get lots of help in convergence because every other term is minus now. Super helpful for convergence. So the harmonic series does not converge, but the alternating harmonic series does. All right, so this leads us to what's called the alternating series test. Alternating series test. Any questions on this? So the alternating series test is this. A series like this is an alternating series, right? When does it converge? It converges if, first thing is, bi plus 1 is less than or equal to bi for all I. What does that mean? What does it mean if bi plus 1 is less than or equal to bi? What could you say about that sequence? What's it doing? What are those values doing? If bi plus 1 is less than or equal to bi. What could you say about that sequence? What as a whole? If bi plus 1 is less than or equal to bi. Yeah, getting smaller, right? This is a decreasing sequence, right? The values decrease. The next one is always less than the previous or equal to. So that's the first thing. And these are the positive. These are the positive components of all the terms, because this is what makes it alternate. And we said bi was all positive, right? So without the alternating, if it's decreasing without alternating, and it goes to 0. The limit of those positive terms goes to 0. So we can put this all together and say we need the bi's to decrease to 0. That's what that's saying. To put those together, you're saying it's decreasing and approaching 0. Then it converges. Then it converges. So remember, if we just had this, if it wasn't alternating, we said this was necessary. Before, we said this was necessary but not sufficient, right? This was necessary but not sufficient. The sequence has to go to 0 in order for the series to converge, but it wasn't enough. Okay? Well, now with an alternating series, that's enough because of the every other is a minus. So with an alternating series, all you need the sequence to do is to decrease to 0. And then the fact that every other one is minus makes it converge. Without the alternating series, we said this was necessary but not enough to confirm that it converges. But with an alternating series, that's enough because of the every other minus. Does that make sense? So this is the alternating series test. If you have an alternating series, all you got to do is look at those positive terms. If you conclude they decrease to 0, it converges. Okay, practice. So here's 2. So these are both alternating series. Alternating series, natural log of 1 over I, and then 1 over the natural log of I. So let's just recall what the natural log function looks like to help you. This is what the natural log function looks like. So I want you to work on those for a couple minutes. I will start attendance. See how those two go. All right, so this is what happens to natural log. What happens as you get close to 0? It goes to negative infinity. What happens as you go to infinity? Does this level off? No, natural log keeps increasing. It keeps increasing, never levels off, so it keeps increasing. Okay, so work on these for a couple minutes, see how it goes. You're either making progress. Okay, Maddie. Any conclusions here? Pick either one. Did you figure out either one? How about Victoria? Okay, why? Okay, that fraction becomes 0. All right, so then we're going to take the ln of a number that's becoming 0. So let's see about that. So that would mean that 1 over I does what? It's going like this, right? Because you said it's going to become 0, right? So as 1 over I does that, what does ln of 1 over I do? What will that go to? So ln is our y-axis here, right? It's the points. This is the points on this graph where if I was here, then the y-axis is ln of I. So I is, as I gets bigger, this input value, goes to 0. So what about ln of I? Negative infinity, right? So what about this? Converge or diverge? By what? So we need justification now. How do we know this diverges? Yeah. Okay, but more than that, so we wouldn't be using, so yeah, because it's not decreasing to 0, we're not using the alternating series test. So therefore we're going to conclude it diverges by something else, right? If this doesn't go to 0, then the alternating series test doesn't apply. Okay? So if the alternating series test doesn't apply, what is it that we're using to conclude that this diverges? What's that? Daniel, see, divergence test, which says what? Right. This is diverges by the divergence test, because what? Because the sequence doesn't go to 0. Remember, that was the very first thing we said. If you have a series and the sequence doesn't go to 0, game over, right? We don't even care about the alternating series test. Doesn't matter. It could alternate or not. It doesn't matter. But if that sequence doesn't go to 0, the series could never converge. So this diverges by the divergence test. That's the justification. How about the next one? How did this go? So 1 over ln of I. Lily, did you get this one? Tell me. Okay. Okay, so the limit is? So as I gets really big, this thing goes to 0. Does it decrease to 0? Yeah, these numbers are getting larger, right? The denominator is getting larger, so the whole fraction is getting smaller. And that's going to approach 0 as I goes to infinity. So, what's our conclusion? What do you think, Lily? Converges or diverges? Converges by what? How do we know that it converges? The alternating series test, right? So here, this one qualifies for the alternating series test because the positive part of the terms decreases to 0 and the thing alternates. So the alternating series test is only a test for convergence. If you have a series that does not qualify, you don't say it diverges by the alternating series test. Does that make sense? The alternating series test will only tell you if a series converges if it meets the requirements. If the series doesn't meet the requirements, then you don't make a conclusion. You just say, I can't use the alternating series test. So that was what happened in the first one.
Excuse me, doctor.
Yeah.
In this example, as Dino said, I should start from 2.
It needs to start from 2. Yeah, sorry. That was just an oversight. So it would have to start from 2 because if I equals 1 gives you 1 over 0. Yep. Good catch. Okay, questions about that? Does that make sense? So again, alternating series test only tells you convergence if the requirements are met. You can never conclude divergence. All right. If the requirements aren't met, then you just use something else. And again, a big reminder here: if the sequence doesn't go to 0, game over. Divergence, the series diverges, and that was the first one. So this is kind of the flavor of these problems you're going to start coming up in the next week. They're all going to be mixed together. We're going to have a series of tests. Or several tests, 5, 6 tests, and then you're just going to get thrown series, and you got to figure out what works. You got to figure out which test applies to determine convergence or not. Can I erase and go on? Any questions? Not happy. Oh, because I'm not in. All right, so let's talk about absolute convergence. Okay, the idea of absolute convergence is, does a series require the alternating help in order to converge? We just saw that, right? We just saw that, like with the harmonic, alternating harmonic series was an example where it needed that help, right, of minus every other term being minus in order to converge. Because if you took that away, then it diverges, right? Just the plain old harmonic series diverges. So, does a series require alternating help in order to converge, or does the series converge whether or not the sum of the terms are negative? Meaning it doesn't need the help. It just always converges, even if all the terms were positive. So absolute convergence is exhibit B. Exhibit B. Absolute convergence means whether or not you make the half the terms negative, it still converges either way. That was what we mean by absolute convergence. So if B, then the series converges absolutely. So what would that be mathematically? So if we had a series, what would we do? What would we do to the series to test if it converges absolutely? Any ideas? Yeah.
Maybe like put an absolute value around it.
Right, around the sequence. To put an absolute value around the sequence. If you put an absolute value around all the terms of the sequence and it still converges, then it converges absolutely. Should make sense, right? So what am I doing? I'm taking any negatives, any terms that are negative, we're making those positive and seeing if it still converges. Okay, so then if it's choice A up there, if it needs the alternating help, then that's what we call conditionally converges conditionally. The series converges, but not absolutely. That was idea A up there. So what is a series that converges conditionally? What's a series that converges conditionally? It converges if it alternates, but it doesn't converge if it doesn't alternate. Harmonic series, right? The alternating harmonic series is conditionally, or converges conditionally. All right, so let's look at some alternating p-series to talk about this. So this would be alternating p-series. Minus 1 to the j plus 1, or j minus 1, doesn't matter. 1 over j to the p, right? For what values of p does the series converge absolutely, conditionally, or diverge? For what values of p does the series converge absolutely, conditionally, or diverge? Let's look at these two examples here. Here's p, alternating p series with p equal to 4. So what do you think? Does this converge absolutely? Does it converge conditionally? Or does it diverge? So we got to know our p series, right? We got to know our p series. So what do we think? Converge absolutely, converge conditionally, or diverge? Samantha, what do you think?
I was thinking, absolutely.
Because?
It's greater than 1.
If she's saying it because p is greater than 1, if p is greater than 1, would we need the alternating? No, right? That's what we learned about, that a p series converges if p is greater than 1. And that was before we even talked about alternating series. So we look at this. So if we put absolute values around this, then it would be 1 over j to the 4th, which converges since p is greater than 1. Therefore, what's the conclusion then? Absolute, conditional, or diverge? Absolute. Converges absolutely. Okay, what about this one? So this is p value of what? J to the what? Cube root, 1/3. Okay, does it converge absolutely, conditionally, or diverge? Trinity, what do you think about this one? Diverges? How come? So p is not greater than 1, so this diverges. Kenny agrees. Steve agrees. Ramiro agrees. Everyone agree? Daniel doesn't agree. Tell me.
I thought that it converges conditionally.
Okay, why?
Because the absolute series does not converge.
Okay.
The alternating series does because the not alternating part goes to 0.
Right, so this is an alternating series. Does the alternating series test apply? We get 1 over j to the 1/3, just looking at the positive part of it. Does that decrease to 0 as j goes to infinity? Yes or no? Yes, because the p sequence converges to 0 as long as p is positive, right? Remember P sequence? The P sequence, that will go to 0 as long as P is greater than 0. So the positive part of our series is going to 0 as j goes to infinity. It alternates. Therefore, by the alternating series test, this converges. But if you took away the alternating part, you'd have a P series with P less than 1. And that would not converge. That would diverge. Therefore, converges conditionally. Do you see it? So this thing converges by the alternating series test. It meets the requirements perfectly. But take away the alternating part, put absolute value around this, you get a series that diverges. It's a P series that diverges. Therefore, this thing converges conditionally. Does it make sense? Anybody? Did I lose you? Please ask. So you got to remember that the P sequence converges to 0 for any positive P. And that means this thing will qualify for the alternating series test. But then when we check for absolute convergence, this goes away. This is the P series with P less than 1 that does not converge. Therefore, conditionally convergent. Questions on this? A lot of silence. I hope that's good silence. I'm not sure. All right, what about the geometric series? For what values of R does the series converge absolutely or conditionally? So what if R was positive, then it wouldn't be alternating, right? It wouldn't be alternating, and so then in what case would we have absolute convergence if R is positive? If R is greater than 0, then these are all the same sign. So the A might be negative. They'd all be negative or they all be positive. So if R is greater than 0, it would converge absolutely if what? So if R is greater than 0, the point is you don't even have to put the absolute value on. They're all the same sign. So when does it converge? Then it's converging absolutely. So when does it converge absolutely? Less than 1, right? If R is less than 1. So the real question here about absolute convergence is when R is between, say, negative, right? When R is negative. Okay, so when R is negative, we can test this for absolute convergence by doing this. Not equals. It's different. This is a different series. We're putting absolute values on it. So.
Could you go over what you just said about
Here?
Yeah.
Well, if R is greater than 0, these are all the same sign. So it just will converge. It'll be absolutely convergent whenever it converges. Right? So there's no, I mean, so if R is greater than 0 and you put this on here, it doesn't change it. It's the same as what you started with. So it will converge absolutely whenever it converges. So as long as it converges absolutely in the case where R is positive. Is that better?
Yeah. And the R is less than what you're saying. It's a fraction.
No, that was our before we ever talked about absolute convergence. This is what made a geometric series converge. Remember 0. So I could do this. It could be -1, but we already said that R is greater than 0. So whenever R is between 0 and 1, for sure it's going to converge absolutely because it's not alternating in the first place, right? It's just not alternating, so it doesn't need alternating help. It just converges, okay? All right, then what about this one? So this one, now R is negative, so we'll throw the absolute values on there. And when we throw the absolute value on there, what do we get? So this is How does this change then? If I put absolute values on all these, it's the same as what? R just being 2/5, right? So now the question is, if this thing converges, then that's absolutely convergent. Does this thing converge? He said no. Agree with that? Geometric series with R equal to 2/5. Does it converge? Yes, converges. Right? Because R has to be between -1 and 1. So, what can we say about this? Therefore, this converges conditionally or absolutely? Absolutely. So what's the overall conclusion about geometric series? Any geometric series that converges, what? Converges absolutely. Doesn't matter. So it doesn't matter if it alternates or not. It doesn't need the alternating, because you take the alternating off, you get an R that's between 0 and 1, and that still converges. Now, of course, if it's outside of -1 or 1, it diverges. So there's not a question of absolute converging absolutely or not, right? Outside, less than -1, greater than positive. Say for you guys, less than -1, greater than +1 means the geometric series diverges, and you don't even talk about it converging absolutely or not. All right. So when it's between -1 and 1, it converges, and it converges absolutely, because it doesn't need the alternating to converge. It would still converge if it was positive 2/5. So all geometric series that converge also converge absolutely. That's the conclusion. Okay, make sense? Any questions? How are we doing? Okay. All right, so here's a test for absolute convergence. So sometimes you can use the definition, like what we just did, to test for absolute convergence. Throw absolute values on there and see if it converges. But sometimes that won't help. It won't work. So here's another test for absolute convergence. It's called the ratio test. So here's how it works. Given an infinite series, we're going to evaluate this. We're going to evaluate this sequence. And this is the limit of the ratio of the I plus first term in the sequence to the ith term in the sequence. So we're going to make a new sequence out of this ratio, and we're going to test the limit of that. And if that limit is less than 1, then the series is absolutely convergent. If the limit is greater than 1, then the series diverges. If the limit equals 1, then the test yields no conclusion. So let's talk about what this is all about. Okay, so this is a generic series for a sequence AI. You see this, you think what? You see this, think what? What do those symbols mean right there? You look like you know, yeah. And what is that? It's a series. And so what does this mean, right? So all these scary symbols, what do they mean? Lauren. It's the right idea, not quite. Riddick. A1 plus A2. And keep going on like that. So I is going to start at 1. We get the A1, A2, A3. Okay, so what? And then we're going to have A. Eventually, we'll have AI. And then AI plus 1. Okay, so what would you multiply the current term by to get the next term? So what do you multiply AI by to get AI plus 1? So we can set up a little algebra problem here. AI times what, x, equals AI plus 1. What is x? What do you multiply AI by to get AI plus 1? Hint, solve for x. What is it?
AI plus 1 over AI.
Right. So given any term, if you multiply by the ratio of the next term to the current term, you'll get the next term. Does that make sense? So given any term, if you multiply by AI plus 1 over AI, you get the next term. What kind of series was that like, where we talked about always multiplying by something to get the next term? What kind of series was that? You remember? Yeah. Is that a geometric series? What's the multiplier in a geometric series? So we've got A plus what? A R plus. Remember this? This is our geometric series. What's the multiplier in a geometric series? R, right? That R is the number you multiply by to get the next. And when does a geometric series converge? Right, when R is a fraction, right? Between -1 and 1. So look, the ratio test is taking the ratio of consecutive terms, which is the multiplier. And what is it saying about that multiplier? If in the long run, that multiplier, that ratio, approaches what? Something less than 1. What's that from? What is that like? The geometric series, right? The geometric series converges when the multiplier is less than 1. The thing you multiply by to get the next term. If that's less than 1, if it's a fraction, then that geometric series converges. Well, so now the multiplier in any given series, it could change, but if in the long run, it becomes something less than 1, if it's approaching something less than 1, then what's happening is essentially it's becoming a geometric series, right? A geometric series means that multiplier is constant, that R value stays constant. But if the multiplier approaches a value less than 1, it's kind of like the series is becoming a geometric series. That's going to a value less than 1, then it's like in the long run, it's like a geometric series. So that's what the ratio test is about. It's asking, does the series morph into a geometric series? Does the multiplier approach some number less than 1? Then in the long run, we have a kind of like a geometric series, and so it will converge. And if that approaches something greater than 1, it will diverge, just like a geometric series. But if it equals 1, then the test yields no conclusion. You have to use something else. Okay? Okay, so does the idea of the ratio test make sense? We're testing to see if the series will become like a geometric series by looking at the multiplier, the limit of the multiplier. And then it's a test for absolute convergence because we're going to look at the absolute value of that, the positive value of that, what we think is the multiplier to get the next term. All right, so let's look at one example quick. All right, so this one. So here's how you do it. So the ratio test says you look at the ratio of the I plus 1 and ith term. Well, here we're using j's, so we'll use j's instead. So the j plus 1 term is -3 to the j plus 1 over j plus 1 quantity cubed. And we're going to take the ratio of that to just the jth term. And we're going to look at the absolute value of that, and then we're going to look at the limit of that. So when you divide by a fraction, you multiply by the reciprocal. And from here on out, you can always start with this step. You can always just start with multiplying by the reciprocal of that down there. So that's our ratio. This is the ratio. This is the multiplier, always the multiplier to get to the next term. So what does it do? So -3 to the j and -3 to the j plus 1 becomes, so I got j plus 1 -3s and j -3s on the bottom. Results in 1 -3, right? There's one more -3 in the top than the bottom, so you just have a -3. Now we got to remember our sequences, right? You have to remember sequences, right? As j gets very big, what will this thing do? We got j cubed over j plus 1 cubed. This will go to what? That will go to 1. We have -3. Absolute value goes to 3 as j gets big. So what's the conclusion? This series is becoming like, as j gets really large, it becomes like a geometric series with r equals 3. Right? This is the multiplier. Conclusion? It will diverge, right? It will diverge because in the long run, it'll be like the geometric series with r equal to 3. It'll get, those multipliers will get closer and closer and closer to 3. We know that diverges because that would be a geometric series that diverges.